The goal of our Predesign project is to look at the confinement of plasma for the purposes of nuclear fusion.
Nuclear fusion is a way to generate energy. Fusion reactors are high-energy reactions in which two lighter atomic nuclei fuse to form a heavier nucleus. When they combine, some of the mass is lost. This is converted into energy, which is in accordance with the formula E equals mc squared. Plasma is a state of matter that is hotter than gas, with all of its electrons stripped from its orbits. Plasma is created before nuclear fusion can happen. This plasma needs to be confined to increase the chance of fusion happening. We need to confine plasma in order to fulfill Larson's criteria. When two nuclei are really close to each other, the strong nuclear force causes the nuclei to attract and fuse, but before that happens, we have to overcome the Coulomb barrier. After the Coulomb barrier has been overcome, fusion will occur. Our objective was to design a system that can more efficiently confine plasma for nuclear fusion.
The Coulomb barrier represents the energy required for a nuclear fusion reaction to occur. It is expressed by the equation energy equals K times Z1 times Z2 times E squared over R, where K is Coulomb's constant, or 8.99 times 10 to the 9th. Z1 and Z2 are the atomic numbers of the reactants, and E is the elementary charge. R is the radius between the two reactants. That is approximately the distance for the strong nuclear force to take over.
The Coulomb barrier can be used to calculate the temperature of the plasma, and in a typical deuterium and tritium nuclear fusion, it's empirically 0.1 megaelectron volts, which can be converted to temperature using the Boltzmann constant, which is 1.381 times 10 to the power negative 3 joules per Kelvin. And when we plug that into the equation, we get 1.2 times 10 to the power of 9 Kelvin, so 1.2 billion degrees Kelvin, which is incredibly hot, which is why we also need to confine it. Device is created with two electrical grids, both connecting to two electrodes of a high voltage DC supply. The grids are configured in a way where there is one larger outer grid engulfing a smaller inner grid, as you can see in the picture. The inner grid is connected to an anode, or negatively charged, while the outer grid is connected to positively charged electrodes. HVDC rips the electrons out of the deuterium and tritium atoms, creating an ion that is positively charged. The electric potential difference of both grids will create enough electrostatic force to accelerate the ionized plasma inwards into the negatively charged inner grid and confine the plasma. This is known as inertial electrostatic confinement. This slide shows the ionization of gas when the machine is turned on. The gases, electrons are being stripped away from its orbits on the outer grid. And this is the image of the fuser being turned on. After a little while, the plasma created on the outer grid has all been confined into the inner grid because of the electrostatic difference. Plasma has successfully been confined in this machine.
Listed are some required courses. They range from plasma sciences and materials courses to electricity and magnetism, as well as atomic physics. Thermodynamics and fluid dynamics are also critical. On the left are some fundamental equations of electricity and magnetism. On the right is them in their differential form.
Some other methods of plasma confinement for fusion reactions are electromagnetic confinement and inertial confinement. Electromagnetic confinement uses magnets to contain the plasma. Tokamaks accelerators are the most common electromagnetic confinement devices. Inertial confinement most commonly uses lasers focused on a pellet of deuterium and tritium to heat and compress the isotopes to induce fusion. These methods of plasma confinement are effective in inducing fusion, but cannot sustain it. The difficulties we face include not being able to completely confine the plasma and neutron bombardment from the reaction, both of which cause damage to the materials used in the reactor.